All right, so take a moment and draw this graph on your notes. I had to draw it in myself. So this is the graph of the second derivative. So make sure you label it. So it crosses here at -1, at 2, at 4, and I've got some asymptotes going on. So pause it if you need to. So what I'm going to look for is where the graph of f of x is concave up. So it's the function that's concave up. And I'm being told that the function is continuous on all reals, so even though there might be asymptotes on the second derivative, the function does not have asymptotes. All right, so where is the graph concave up? So between -infinity and -1, the graph of the second derivative is above the x-axis. Between 2 and 4, the graph of the second derivative is above the x-axis. And where is the graph of f of x concave down? Between -1 and 0, and 0 and 2, and 4 and infinity. All right, so now I'm going to be looking for the points of inflection. Those x values where the concavity is changing. So the concavity changes from concave up to concave down because the sign changes from positive to negative at x equal -1. At x equals 0, before 0 and after 0, it's negative. So that is not a point of inflection. After 2, the second derivative is positive, before it's negative, so x equal 2 is a point of inflection. And before 4, it's positive, after 4, it's negative, so 4 is also a point of inflection. All right, so now we're going to look at the second derivative test. So the first derivative test and the second derivative test give you, therefore, a y value is a local min or max. So let's look at what part A is saying. Part A is saying if you have this kind of a critical number, so that kind of a critical number means if I have this point C, that the slope of the tangent line is 0. Slope of the tangent line is 0. And this is saying that at that point C, it's cupped up. So if I know the slope of the tangent line is 0 and it's cupped up, can you see that f of c must be a local minimum? You can visually see it. Part B is saying if I've got this point C and the slope of the tangent line is 0, and I know the graph is cupped down, it's cupped down, I can see that f of c is going to be a local maximum. So notice this only works for this kind of a critical number. If I have the kinds of critical number where the derivative doesn't exist, this test does not work. So the second derivative just tells us shape. The second derivative test combines critical numbers with shape to tell us if we have a max or a min. All right, so let's go to this one here. So I need critical numbers. So let's start off with the derivative. Set it equal to 0. So I get x is equal to pi over 3 and 2 pi over 3. So those are my two critical numbers. Now I need to go find the second derivative. So that will be negative cosine of x. So I take, and I can either do it by the graph or I can evaluate it. So I take pi over 3 and I substitute it into the second derivative. And I take 2 pi over 3 and I substitute it into the second derivative. So I'm looking to see if this is positive or negative. I don't need to know if it's what the number is. So if I plug in pi over 3, so negative cosine of pi over 3. So cosine of pi over 3 is positive. This gives me a negative number, so this is less than 0. So less than 0, so I get the conclusion that f of pi over 3, because it's concave down, this must be a local maximum. If I plug in 2 pi over 3, I get negative cosine of 2 pi over 3. This is negative, then it turns positive, so I get a bigger than 0. So that means that f of 2 pi over 3 is a local minimum. All right, so now we're being asked to find the intervals of concavity. So that's where I look at the second derivative. I can look at the graph, or I can look at number line. I'm going to look at the graph, so I know between 0 and 2 pi, again, that's where we're being asked to look, between 0 and 2 pi, this would be the second derivative graph, and I know it is 0 at pi over 2 and 3 pi over 2. So where the graph of f of x is concave up, remember we're talking about the function, not this second derivative graph, right? The function is concave up is when the second derivative graph is above the x-axis. And where the function is concave down is where the second derivative graph is below the x-axis. And our points of inflection are going to be those x values where the concavity is changing. So the concavity changes at pi over 2 and at 3 pi over 2. We have negative to positive and then positive to negative. Okay, so we've got all these pieces of information. So let's see if we can put together a sketch of a graph. So I've got between 0 and 2 pi, I've got pi over 3, pi over 2, 2 pi over 3, and 3 pi over 2 as points that I need to think about what's happening. So at pi over 3, I have a local maximum. And I'm not going to worry about the y values. I could go plug it back into the original function. I'm just looking for just a good shape of the graph. So I think it's going to be a maximum at pi over 3, nice slope 0 up there, and then it's going to be a minimum at 2 pi over 3 down here. And at pi over 2 in between, it's going to be changing concavity. So changing concavity, so we're going to have it changing concavity right there. And bringing it down, slope 0, and then it's going to be changing concavity again at 3 pi over 2. So here, you just have it changing concavity. So I'm just going to put dots where I've got it changing concavity, so you can see my points of inflection. So maximum here, minimum here, points of inflection labeled. So pi, pi.